Alright, we have shown that the stability criteria for the Euler method to solve this ODE is given by this expression over here. Of course, if you look at this expression, the h that you need to define depends on your constant k. So constant k can be either positive or negative. So when you select your h, it would have to depend on the constant k that you have. So for example, if k is positive, it means that this condition will just be true. You have minus 2 over k, and your h must be larger than that and less than 0. So for h to be less than 0, it means that your h has to be negative. But having a negative step size do not make sense in your Euler method. So this means that because h is negative, your Euler method will fail. So what we can say is that in the case where you're solving this ODE and k happens to be a positive number, the Euler method to solve this ODE is what we call unconditionally unstable. Okay, because regardless of what h value that you use, you will never satisfy the condition where h has to be negative. So the Euler method will fail because the method or the algorithm that you use is going to be unstable. So that is the case if your k is positive. What happens if the constant k is negative or less than 0? Now, if the constant k is negative, we can also write k as minus c, where c is a positive number. Okay, so defining c as a positive number and introducing a negative in front ensures that k is going to be negative. So if k is negative, what happens to your stability criteria here? You have minus 2 over minus c to be less than, you have h here, and you have 0. Okay, so alright, sorry, before you do that, you can actually apply this particular criteria because k here is now minus c. So you will have to use this expression over here. Okay, so rather than using this, we are going to use minus 2 hk and 0. So in this case, if k is minus c, you're going to get minus 2 to be this times h negative c 0. Alright, so if you bring the c over to the left hand side and right hand side, you flip the signs, you get h to be greater than 0, but it is less than 2 over c. So right now your h is definitely positive because of this condition over here. However, it also says that your h has to be less than or equals to 2c in order for your algorithm to be stable. So depending on what the value of c is, so that depends on the problem that you have. Depending on what value of c that you have, as long as you select a step size to be less than 2 over c, your algorithm is going to be stable. So before I move on, I want to mention that some of the textbooks or lecture notes that you see may implement or may write the stability criteria as minus 2 less than hk less than 0. So they basically omit the equal sign. So omitting the equal sign is also fine. Having the equal sign basically says that you're approaching the threshold where your algorithm is going to be stable. Okay, so of course, if h is less than or equal to 2 over c, and let's say c is 100, it means that h has to be less than or equal to 0.02. So selecting h equals to 0.02 may not necessarily guarantee a stable criteria, because you're using a very strong criteria that is very close to the threshold for stability. So there will be an example later on that where I'm going to demonstrate this. Okay, so what I'm trying to say here is, if you want to write your stability criteria without the equal sign, that is perfectly acceptable. Okay, alright, so we have already shown that the stability criteria is given by this. However, the condition that I mentioned is this is only valid for dy dt is equals to ky. What if we have a more generic ODE, a more general ODE? Let's say dy dt is equals to f as a function of t and y. So this is the ODE that we used to see in the previous lectures. So if the right hand side is given by this, it means that we can also write fty to be equals to ky. Okay, so from using chain rule, we can see that the partial derivative of f with respect to y is basically the partial derivative of the right hand side ky with respect to y. So if you differentiate this, this is going to give you k dy over dy plus y dk dy. Because k is a constant, this becomes 0, dy gives you 1. So this tells us that k, which is generic in our derivation before, is simply given by df dy. So if k is given by df dy and we have a generic ODE like this, the stability criteria can be written then as -2 less than h, df dy less than 0. Okay, so the stability criteria for your Euler method for a generic first order ODE in this form is given by this expression over here. Okay, so this criteria that you see is valid only for the Euler method. Of course, if you're going to use some other methods, let's say the Heun's method, midpoint method, or even the Runge-Kutta method, the stability criteria is going to be different. For example, for your RK4, the stability criteria is given by -2.785 times HK, to be less than HK, and HK has to be less than 0. So this is for the RK4 method. Of course, the derivation is a lot more complicated than what you see with the Euler method. So you don't have to worry about deriving this for your particular unit. Alright, let's consider an example. So let's say you have an ODE that is given by dy dt equals to 12 times y squared. So your right hand side is 12y squared. You are asked then to determine the stability criteria for the ODE above using the Euler method. So we already know that the general stability criteria for Euler method is given by this equation over here. So if you look at your right hand side of your ODE, the right hand side f is essentially given by 12y squared. So to find the stability criteria, you need to find the partial derivative of f with respect to y. So this is simply just 24y. So if this is 24y, what then becomes of your stability criteria? It becomes -2 less than 24 hy, and this must be less than 0. Okay. So if you look at this, if you take first this condition over here, it simply tells you that h has to be negative, and if h is negative, it means that your Euler method becomes invalid. So having h equals being negative will just tell you that your algorithm is going to be unstable. So we are not interested in this because this does not apply. So on the other hand, we would have this condition over here. So here you're going to have 24 hy to be greater than -2. So what is h, which is the step size that we're interested in? H becomes larger than -1 over 12 divided by y. So this basically says that in order for you to solve this ODE subject to a given initial condition, the selection of a step size h must be satisfying this criteria here. However, if you look at this stability criteria, your h must be greater than -1 over 12y. What is y? Y is essentially your solution that you're going to get for your ODE. So this means that your step size, in order for you to guarantee stability, actually depends on your solution. And if your y changes, your stability criteria is going to change. So your stability criteria will change as your solution, as you move along in your solution. All right. So from here you can see that different problems will give you different ways of analyzing a stability criteria. Even though if it's just the Euler method, we know that it's in this form, but if you have different functions, you may get different solution. So for example, if you look at this plot over here, if you look at this solution, you have the same ODE that is being solved with two different initial conditions. So the plot on the left, where on the top window here you have the error, and at the bottom you have the solution of y with respect to t, you can see that as the time increases, as you move along in your time step, the error will keep on increasing. So this is an indication that your algorithm is unstable. However, when you look at the column to the right, when you use a different initial value for the same ODE, you can see that initially the error increases. However, as time goes on, the error decreases. So this is one of the characteristics of problems like this, where your step size actually depends on your solution Y. So in this case over here, the solution or the algorithm that you get for any early stages of t is going to be unstable, but as you move along in the solution, the stability criteria perhaps relaxes. So in this case, the solution that you get is still acceptable, because beyond a certain period, the algorithm becomes stable.